So last time we started discussing inner products or other inner product spaces, and inner product space is a vector space over a field which, for this purpose, we would be taking to be either reals or complex numbers, and it's equipped with some kind of an inner product function which satisfies these three properties. That it's like a linear transformation in the second input if you fix the first one, flipping the order of the inputs conjugates the function, and the inner product of a vector with itself is a non-negative real number, which is 0 if and only if the vector is 0. And yeah, we also saw some other nice properties, like it's conjugate linear or anti-linear in the first coordinate. And then we prove a couple of useful inequalities. First one I sort of sketched the proof of, which is the Cauchy-Schwarz-Bunyakovsky inequality, commonly known as Cauchy-Schwarz. And there are two equivalent ways of writing it. So we can basically define the inner product of a vector u with itself with a square root to be some sort of notion of length or distance from the origin. And it's kind of a good notion of distance in the sense that it follows the so-called triangle inequality, which says that the distance from u to w is at most the distance from u to v and v to w. So you can always go through v, and that can only be longer. Okay, and this one I left as an exercise, but it's an important inequality to know. And in case you're having any trouble kind of proving it, feel free to ask, and then we can go over it. Okay. All right. That's just a reminder of what we were doing last time. Any questions come to mind? Anything that you'd like to discuss? If not, you can always stop me later. Okay. So today, I want to continue our discussion of inner products and specifically talk about the case when the inner product is 0, which is quite interesting in terms of what all it implies. We say two vectors u and v are orthogonal if their inner product is 0. Yeah. And again, this is being stated for any inner product space with any valid inner product. So I'm omitting any kind of subscript here. It's just written with this notation of angular brackets without any mu. It works for any function mu which is a valid inner product. Okay. So we'll say specifically that they are orthogonal under that inner product. We will say a bunch of vectors in a set S are mutually orthogonal if any two of them have inner product 0, as long as we are looking at two different ones. A vector may not have inner product 0 with itself. Okay. In fact, yeah, based on the third property, a non-zero vector can never have inner product 0 with itself. Okay. And the third is a vector is or sort of a set of vectors is orthonormal if the vectors are mutually orthogonal. So whenever you look at two different vectors, the inner product is 0. And whenever you look at the inner product of a vector with itself, or its sort of norm, which is the square root of the inner product, you get 1. So any two things are orthogonal to each other, and everything has norm 1 or the length 1. Okay. But this norm again is defined with respect to whatever inner product we are dealing with. Okay. And let me just sort of okay. we'll get to another notion later. Right. Any questions about these definitions? So just inner product 0 for orthogonal, and orthonormal is just the inner product with itself is 1 and with everything else is 0. All right, so let's see a couple of examples. Let's start with, let's say, a vector space which is R2 equipped with the usual inner product, which is the coordinate-wise dot product. I will often refer to this as the usual inner product or the standard inner product. So this I may not always explicitly specify and just call it the usual one. And you can see the vectors which are 0, 1 or 1, 0. So it's 1 in one coordinate and more generally 0 everywhere else if the dimension is more than 2. These are orthonormal. With itself, you get 1 with sort of any 2 vectors of this form. In fact, they form an orthonormal basis because there are 2 of them, and we'll see in a minute that they are actually also linearly independent. Well, for these vectors, you probably already know that. And this is sometimes also referred to as the standard basis or the coordinate basis. For R2 or more generally RD, when you have vectors in which one, because if you write something as a linear combination of these, then the coefficient of 0, 1 will be just the y coordinate of your vector, and the coefficient of 1, 0 will just be the x coordinate of your vector, and so on. So in this basis, the coefficients are the same as coordinates. Okay. This, I'm guessing everyone sort of is familiar with, but if not, yeah, I can go over more details of this example. Now let's consider a slightly different inner product. So the space is still R2, so 2-dimensional vectors with real entries. But now I'm going to change the inner product, and this is an example we talked about last time. I claimed that this forms, or actually I proved that this forms an inner product. And now I'm asking, can you find me maybe 2 vectors which are orthogonal or orthonormal, depending on whatever you want to find, under this inner product. And for starters, maybe even check if the vectors we produced earlier for the R2 with the standard inner product or the usual inner product are still orthogonal or not. Any guesses or proofs, answers? Okay, let's start with the vectors we already have. So these vectors 0, 1 or 1, 0. Are they still orthogonal? Can try yes or no, type in the chat or speak up.
Should be no, right? Because
right. So these vectors are not quite orthogonal. So if we sort of write with x equals 0, 1 and y equals 1, 0, then x inner product y, the x1, y1 and x2, y2, x2, y2 terms will be 0, but then we will get this part, and I guess x2, y1 is 1, so we get half. So they are no longer orthogonal. So, I mean, one observation which is kind of clear that vectors which are orthogonal under one inner product may not be orthogonal under another inner product. That's why it's a different inner product. So orthogonality is a property of the inner product. I claimed that they form a basis, or in particular, there were two linearly independent vectors in R2. Are they still linearly independent? Yes, no.
Is not a property of
What do you mean?
dot product.
Okay, something in the chat. Yes, there's still, in fact, I mean, I didn't even need to ask the question, in the sense that linear independence has nothing to do with inner products. We define linear independence just in terms of whether you can have a linear combination which is equal to 0 or not. And if a linear combination of these two vectors was 0, it will remain 0 no matter how we define the inner product on the space. And if no linear combination was 0, you still won't have it. So linear dependence and independence are not actually directly related to inner products, although we'll see that inner products give us a convenient way of talking about linear independence. But so this is still a basis for this new space. In fact, a basis remains a basis no matter what you do with the inner product. But it's no longer an orthonormal basis. In particular, the vectors are not even orthogonal. Okay. All right. It's not obvious how to immediately find vectors which are orthonormal now under this inner product, or maybe it is obvious to some one, but yeah, it's not obvious to me. And what we will see is that there is kind of a generic way of just starting with linearly independent vectors and creating orthonormal ones. Okay, and then we'll see that in a minute. So there is, in particular, you can start with these two vectors which you know are linearly independent, and actually there is a simple procedure to compute an orthonormal basis for this space starting with them. So and then we'll get to it. Okay. So just to illustrate that linear independence always is not a property of the inner product, and the orthogonality is, it can change. Okay. Now here is the relation between orthogonality and linear independence, that if you do have a set of mutually orthogonal vectors, then they are linearly independent. So it's a sufficient condition. It's not necessary, as we just saw, but it's a convenient way of proving linear independence if you know that things are orthogonal. Okay. And the proof is more or less just sort of following our nose in terms of the definition of linear independence. So let's say that's not the case. So So then there exists some vectors v1 to vn in the set, coefficient c1 to cn in whatever field we are working with. And this can be either reals or complexes now, such that c1 v1 plus c2 v2 okay, and the coefficients are kind of non-trivial, so not all of them are 0. And we can now kind of easily violate this, or we can easily prove that, well, all coefficients must be 0 just by taking inner product. So let's say we take an inner product with vi, with any vi. So I is the index of one of these vectors. And so I get the inner product with vi on both sides. And now by linearity, I get that C1 times the inner product of vi with P1 so Cn times the inner product of vi with Pn is equal to 0, because the inner product with vi is a linear transformation on the second input. Linear transformation is always 0 when you plug in 0. So the right hand side is 0. Now, these are vectors are mutually orthogonal. So we know that vi inner product vj is equal to 0 when I is not equal to j. So the only term that will survive is ci times vi inner product vi. We get 0 on the right hand side. Now this is in particular not 0, because vi is non-zero, and that's because we are starting with a subset of vectors where none of which is the 0 vector. So vi is not the 0 vector, so the inner product with itself must be non-zero, in fact even positive, and so ci has to be 0. And what we just did, we can repeat for any I that we want, and so all the coefficients are 0. So the only way you can have a linear combination which is equal to 0 is just a trivial one. All coefficients are 0, nothing non-trivial can work, and so the vectors are linearly independent. Okay, right? This is sort of just following our nose with the definitions of orthogonality and linear independence that we have. Any questions? Okay, so now let's go back to this issue of finding an orthonormal basis. And so here we know something very nice, that so previously we said if you have an orthogonal or mutually orthogonal set of vectors, then they are linearly independent. You can also go in the other direction, that if you have a set of linearly independent vectors, you can make them all mutually orthogonal, or you can sort of find another set of vectors which are mutually orthogonal, in fact orthonormal, with the same span. So in some sense they kind of produce the same kind of information, or their linear combinations specifically will produce all the same vectors. Okay, so you can sort of convert this linearly independent set into an orthonormal set, which sort of gives you the same sort of information. Okay, and is sometimes nicer to work with, as we will see. Any questions about the statement? So, okay, and we'll prove it by induction on K. So we will prove that for every K, there exists orthonormal W1 to WK, which have the same span as V1 to VK. When we reach K equals N, we'll be done. Okay. Let's start at k equals 1 though. So I'm given V1. It's linearly independent. Well, it's just one vector, but linear independence just means that it's a non-zero vector. So it's not equal to 0. I need to find W1. Now, W1 doesn't need to be orthogonal to anything because there is nothing else. I just need to find W1, which has norm 1. Okay. So here, I can just take it to be V1 divided by norm of V1, which is non-zero because V1 is non-zero. Right? That's the one conclusion I do get from linear independence of a single vector. And so then by linearity, the inner product of W1 with itself is V1 inner product of V1 with some scaling with itself. And again, by linearity and anti-linearity in the second and first coordinates respectively, I can pull these numbers out. And I have an inner product of V1 with itself. And of course, the norm of V square is just a shorthand for inner product of V1 with itself. So this is just 1. Okay. So yeah, this is just a sanity check that you can at least do it with k equals 1. Now let's get to the more interesting part of this induction that I want to prove. So suppose, so I already know that there exists W1 to Wk, which are orthonormal. And the span of W1 to Wk is equal to the span of V1 to Vk. The goal is to find Wk plus 1, which maintains this kind of span property now with V1 to Vk plus 1 and has norm 1 is orthogonal to all of W1 to Wk. Any questions about what we want to do? It's okay, so let's, this is manipulation we do, we will end up doing quite often. So to define, so we need to define Wk plus 1. And we'll actually compute it in 2 steps. So first, let's find Uk plus 1, which will be orthogonal to everything, but will not necessarily have norm 1. And then we will change it to norm 1. So Uk plus 1 will be just Vk plus 1 minus, let's see, which way do I want it? Inner product of I'll claim that this is orthogonal to everything else and has the same span, and we'll get to it in a minute. And then I'll define Wk plus 1 just to be the appropriately scaled version of this so that the norm becomes. Note that this can be done, we are claiming this can be done in any inner product space. So when we are working with real vectors, you may probably seen this operation, but more interestingly, this can be done for spaces of functions or spaces with any kind of interesting inner products that you might have. So in particular, even that two-dimensional example that we saw, we can create an orthonormal set of vectors with the same span as 1, 0, 0, 1, which is everything, which is all of R2. Okay. So now I need to prove that UK plus 1 is orthogonal to all the WIs. The WIs from 1 to K just remain orthogonal to each other. And what I need to prove is that the inner product of WI with UK plus 1 is equal to 0. And so let's just compute it. I'll just use linearity. Okay, let me use J for this index, or rather, let's use J for the index here so as to not get confused in the summation. And because the W's are an orthonormal set, this is equal to 1 if I is equal to J and 0 otherwise. So there is only one of these terms that survives, which is when J is equal to I. Oh, sorry, this was J. Because J is equal to I can write this. And this is equal to 1, so the whole thing is 0. And I claim that I'm done now. So I kind of had these other things about the span of the W1 to WK plus 1 being equal to the span of V1 to VK plus 1. I claim that just this orthogonality is sufficient to show all of the things I need. That's because note that the vector we found, WK plus 1, is in the span of VK plus 1 and all the Ws. Anything which is a linear combination of W1 to WK can be written as a linear combination of V1 to VK. So it's in the span of V1 to VK and VK plus 1. So now this W1 to WK, W1 to WK plus 1 are K plus 1 orthogonal vectors and hence linearly independent. In this span, the span is K plus 1 dimensional, or at most K plus 1 dimensional, but because I found K plus 1 linearly independent vectors, it's exactly K plus 1 dimensional. And because I have the right number, they are a basis and their span is equal to the entire span of V1 to Vk plus 1. So their span is correct. They're all orthogonal. And I, again, normalize Wk plus 1 so that norm becomes 1, just as we did for the case of k plus 1. So I have W1 to Wk plus 1, which are orthonormal, have the same span as V1 to Vk plus 1, and we're done with the induction step. Any questions? Okay. So this is a fairly simple, and yeah, as an exercise, you can go back to the problem we saw, then find an orthonormal basis, and I will just use ON as a shorthand for orthonormal. So the example we saw earlier, maybe it's good to try and find an orthonormal basis for it. Okay, this actually has a very nice corollary, which that if you have a finite dimensional inner product space, so it can have any inner product defined on it, and we are going to only state this for finite dimensional spaces for now, then it has an orthonormal basis. So for vector spaces in general, we said that every vector space has a basis, and if you have finite dimensional vector spaces, then it's kind of easy to find this basis. Otherwise, you need this sort of action of choice stuff. And when you have inner products, you can get even nicer properties that you don't just have a basis, but you have an orthonormal basis. And the proof is just sort of what we said so far, is that, well, we already know it has a basis. The basis is a linearly independent set whose span is the entire space. When you apply Gram-Schmidt, you will get an orthonormal set whose span is the same as the span of the basis elements, which is the entire space. So just start, you know it has a basis, start with it and apply Gram-Schmidt. This also has a nice consequence for Hilbert spaces, which we briefly discussed last time, which is the inner product spaces, but where you also include any kind of limit points of any sequences of any converging pushy sequences. So again, we won't necessarily need Hilbert spaces, but I'll keep referring to what statements are true in the infinite case, sort of if you are interested. But for the purposes of the course, we can stick to finite dimensional inner product spaces, and that's all I'll need in terms of exams and homeworks, etc. But yeah, in case you're curious, you can also show, again, using some axiom of choice, or like, again, using Zorn's lemma, is that every Hilbert space now also has a countable orthonormal basis. But this is a slightly different notion of basis. So remember previously when we said we have a basis, we only allowed finite linear combinations because we didn't know how to make sense of infinite sums. We didn't know how to say convergence because we didn't have a notion of distance, etc. In Hilbert spaces, we can do all of that. In abstract vector spaces, we can't. So here we will allow infinite sums, and then you get this kind of nice orthonormal basis. And infinite sums are just defined as limits of a series. In fact, these are countable. So this basis itself is a countable set. And this is called the Hilbert basis. Okay. Any questions so far? Okay. So what did we do so far? We kind of proved that you can start with a linearly independent set and get an orthonormal set. We can start with a basis, get an orthonormal basis. And we can do this for any inner product space, at least for finite dimensional ones, and also for Hilbert spaces if needed. And orthonormal bases are kind of a much nicer kind of basis when you want to talk about linear combinations, when you want to reason about what information you can get about a vector by looking at the coefficients in the linear combination. And in particular, when you have an orthonormal basis, these coefficients are called Fourier coefficients with respect to this basis. Okay. And I mean, more generally, if you have seen Fourier analysis and so on, depending on what setting you saw it on, maybe sine and cosine functions, these can form some particular orthonormal basis for functions over the, let's say, interval 0 to 1 or 0 to pi, depending on how you want to define it, or for periodic functions, etc. And these or maybe if you saw discrete Fourier analysis over some groups, then there are certain functions which again form an orthonormal basis. But in general, you can define Fourier coefficients as just coefficients for basis vectors when you have an orthonormal basis. Okay? So you don't need to worry about any of those special kinds of Fourier and sort of analysis settings that you may or may not have encountered. Okay, let's just go back to this one. You have an orthonormal basis, fix any orthonormal basis W1 to Wn for some space V. So now it's n-dimensional. And I claim that for any vector V, there exists coefficient C1 to Cn, such that I can write V as a linear combination of W1 to Wn with these coefficients. Why? Because, well, V is in the span of W1 to Wn. It's and so when something is in the span, it just means that you can write it as a linear combination. Moreover, because the W's form a basis, these coefficients are unique. Because if you had two different ways of writing V as a linear combination, then you can subtract these two different ways and you will get a linear combination of just the basis elements, which will be equal to 0. And because they're linearly independent, that's not supposed to happen. So C1 to Cn are in fact unique coefficients, and these are called the Fourier coefficients of V with respect to this basis V. And you can actually compute them. There is some very simple way of computing them when you know that the basis is orthonormal. And let's just a sanity check. So we know that V is summation Ci times Wi. So now I claim that Ci is equal to Wi in a product V. So let's just compute this in a product. Okay. Again, maybe I will use J here so as to not confuse. This is just the local index. So inner product of Wi with V again by linearity of the inner product and the second input. And it's the same property again, that this is equal to 1 when I is equal to j and 0 otherwise. Because the W's form an orthonormal set. So the only term that survives is when I is equal to j, and that's Cj. Okay. And what we started with was, of course, Wi inner product. So we just get a way of computing these coefficients. All you need to do is take an inner product with the appropriate basis vector. Yeah, when you're working in the field of complex numbers, you may want to be careful whether you put the basis vector in the first or second coordinates, otherwise you'll get the conjugate. So yeah, nothing too bad. Okay. So then once you have an orthonormal basis, you can easily write any vector in terms of this orthonormal basis. And also do other things like compute the inner product just using these coefficients or in terms of this orthonormal basis vectors. So this is just a consequence of what we said, that the coefficient can be written this way. Yeah, let's just check. So maybe let me write something on the previous page. So because the coefficient is this, it just means that for every vector, you can write it in this unique way. So you can write it as summation Ci Wi, but we know what Ci is. It's the Wi is inner product V times Wi. So we calculated the values of the Ci's, so you can write every vector just in this way. Once you have that, you can compute inner products this way. So you want to calculate, let's say, the inner product of U and V. Well, we know what U is. It's summation over I from 1 to n. Some coefficient which can be computed this way times Wi. And we know what V is. It's some coefficient which can be computed this way. And again, we will open it up. We will get n square terms now. And I'm going to use antilinearity or conjugate linearity in the first coordinate. So the first input, linearity in the second input. And they will be left with an inner product of Wi and Wj, which again is 1 if I is equal to j and 0 otherwise. So the only terms that survive are the ones when I is equal to j, and so I get summation over I. Okay, which is what I get. Now, let's kind of maybe reinterpret what we just proved. So we sort of define this inner product with kind of making a big deal that, okay, there is this usual inner product on RD that you might be used to, which is the coordinate-wise inner product for complex numbers where you kind of write x1 conjugate y1, x2 conjugate y2, etc. But there are more general inner products, and there's kind of, yeah, many other inner products you can define for functions, whatnot. I gave a few examples. Then I kind of said, okay, now if you have an orthonormal basis, and if you have the Fourier coefficients, so if, let's say, C1 to Cn are the Fourier coefficients of U, and D1 to Dn are the Fourier coefficients of V. Okay. I mean, we computed these values. These Fourier coefficients are just equal to the inner products. So then we just said, well, you can still write it as a coordinate inner product, except that now these coordinates are replaced by these Fourier coefficients. Okay. Or rather, if you kind of think in the basis of these orthonormal vectors, then basically every inner product is just, so for every inner product, if you find the right, or find an orthonormal basis for this inner product, then the inner product is basically again a coordinate inner product. So so every inner product can be written as sort of like the standard inner product on complex spaces that we started. Okay. So then what's the big deal? I mean, why kind of talk about this whole shebang of trying to go to some weird inner products, then trying to compute some weird orthonormal basis, and then we are back to coordinate inner products. The point is that for whatever vector space you have in mind, it might be more convenient to work with one kind of orthonormal basis than another kind of orthonormal basis. And the inner product that you are working with, if you find the right orthonormal basis for it, then things become much more convenient. So in some sense, inner product is used to define distance. The notion of distance we might have in mind may depend on the application. We want to think of two functions and how far they are. Maybe we care more if they kind of maybe we just want to know how many inputs do they differ on. Maybe we care more about inputs closer to the origin and care less about inputs farther from the origin, or whatever else notion of distance we might have in mind. So inner product is usually governed by what is the notion of distance we have in mind for our application. So we can't always choose it to be the standard inner product. But then what Parseval's identity tells us is that, well, no matter what inner product your application needs, find an orthonormal basis and then you can be pretty much back to coordinate inner products. Okay? So you can do whatever manipulations you are familiar with, just find the right orthonormal basis. And in some sense, in a very maybe kind of cartoonish way, a lot of Fourier analysis is just saying that, well, there is some nice basis, the so-called Fourier basis for functions, which again, you may or may not have necessarily seen before, but we'll give some examples later. And once you are down to that basis, you can do all kinds of nice manipulations with this basis. So, and yeah, I mean, this is true for other inner product spaces. Okay. Any questions? All right. The next concept I want to define is also related to inner product spaces, but now it's kind of related to two inner product spaces, not just one. And inner product spaces which over the same field. So again, either reals or complex, but it's the same for both V and W. And for a linear transformation phi, which maps V to W, we'll say phi star is an adjoint for phi, or adjoint of phi, if it kind of maps in the opposite direction. So we can't quite take inner product of one thing from V and one from W, because these are like apples and oranges. And so if phi maps apples to oranges, the phi star maps oranges to apples. And so that you can always take inner product of either apples and apples or oranges and oranges. And it maps in the right way. So if you wanted to compare W and phi of V, if you wanted to take the inner product, you can look at W and V. You can compute phi of V so that you now have something in the right space to take inner product with W and take the inner product. Or you could go the other way. You can sort of look at W, map it back to the V space and take the inner product there, and you're going to get the same value. So kind of instead of mapping the apple to the right orange, it maps the orange to the right apple so that you can take the inner product property. Okay. That's just yeah, and we'll see that in some cases these are very simple. So let's start with vector spaces over reals, the usual or the standard inner product coordinate wise. And let's say A is a matrix. So as we saw earlier, a matrix can just be thought of as a linear transformation. And if we think of vectors as column vectors, then it's mapping Rn, where n is the number of columns, to Rm, where m is the number of rows. And the inner product of W with the linear transformation of V is just, so W is, let's say, a column vector in m dimensions. So the target space, or the space where the images lie for phi, is W, or is Rm. So it's a column vector. So let's take the transpose times phi of V is just the matrix times V. So it's a column vector now with m rows, and so W transpose A times V is just the dot product or the coordinate wise product. So this is just another way of writing the product. And what we want is phi star, which maps the other way around. So we can think of it as a matrix B, which now has n rows and m columns, such that for all V and W, the inner product of phi star of W, which is now B times W transpose times V, is equal to the inner product of W with phi of V, which is W transpose AV that we just saw. Any guesses for this, what this matrix B should be? Right, so let's just open this up using the rules for transpose. So we get this is equal to W transpose B transpose times V. And we want it to be equal to W transpose AV. So yeah, as someone already pointed out on the chat, you can take B transpose to be A, or rather B to be A transpose, right? So remember, we didn't say necessarily that there is only one such adjoint, but certainly B equals A transpose works. It will turn out that this is the unique adjoint, and especially when you have finite dimensional inner product spaces, you will have this unique adjoint property. Okay. So, but this is just a kind of fancy generalization, if you will, for the transpose of a matrix. Okay. But this is sort of a concept which makes sense for any inner product space, where you may not always be able to write your linear transformation as a matrix. All right, so, and so far we haven't even claimed that it always exists, etc., but we'll get to that. So let's start with let's go to another example. All right, so now let's say we again have two inner product spaces, V and W, space of functions. So we kind of have used this notation before. This is the space of continuous functions from the domain 0, 1 to the range -1, 1. And this is again, let's say, space of continuous functions from the interval 0 to half to -1, 1. And we define inner products as kind of just of two functions as integral over whatever space they are defined on. Okay, and this is an example we kind of briefly talked about when defining inner products. And phi, so yeah, we need to define a lot to get to the point of computing an adjoint. So we need to define two spaces, their own inner products, which can be different, and this linear transformation which maps it. So here the linear transformation is that phi of x, which is, let's say, some function g, now lives in the space where the domain is only 0 to half. Maybe did I make a mistake? No. So this is, let's say, some g, and if I want to compute g of x, I'm only allowed to do this for x which is between 0 and half, because g lives in this space w. Okay, I will compute it by computing f of 2x. 2x now lives between 0 and 1, and it's a valid input to f. And this is again something we talked about. This is a linear transformation. In fact, you can do more crazy operations to x and you still get linear transformations. And the question is, can you find a map which has this inner product, which preserves this sort of inner product property? Okay. Right? You can try it. In fact, let's take a 2-minute break and you can continue, and we'll see what this is. Any guesses to what the adjoint might be? Let's remind ourselves of what is the property of the adjoint that we want. We want that for every u and v, the inner product of let's say v and w, just to be consistent. W with phi of v is equal to the inner product of phi star or phi star of w with v. And let's write down what we know about the inner product of w and phi of v. So this is and yeah, I guess maybe this is something I should have emphasized even earlier. These two inner products are in different spaces. So this inner product is of w with phi of v, which are both in the w space. So this is in the inner product in the space of vector, in the inner product space capital W. And this is an inner product space capital V. So as I was saying earlier, I guess one is in the space of apples and one in the space of oranges. Okay, so now let's write down these inner products. We want to compute the inner product of W. Let's say, let's think of V as some function f. In the first space, let's think of this as some function g. And what we are saying is that in the space of g, the inner product of g with the linear transformation of f should be equal to the inner product in the space of f. Let's say this is some other function h, and we'll need to compute, we'll need to figure out what h is. is equal to the inner product in the space V of h of x, or maybe let me just use a different variable here to clarify, times f of y. And it's sort of, when you write it this way, it's not it's sort of close to what you want. You can see what we need just by doing a change of variables. So now let's substitute let's do a change of variable in this integral. So when x goes from 0 to half, y goes from 0 to 1, you get g of y divided by 2 times f of y, and dx, which is now dy divided by 2. And I will write that half here. So we just match this form of the integral. This is what we want. So in particular, if you have the linear transformation, which maps every function at input y, half of g divided y divided by 2, that serves as an adjoint. Okay. As an exercise, I'll ask you to compute the adjoint when, again, for our favorite left shift operator on the Fibonacci space, etc. So we've talked about this space quite a lot. And try computing the adjoint of this. In fact, there is, in some sense, also a recipe for computing the adjoint. So we'll see it in a minute, but at least for finite dimensional spaces. And yeah, we'll see why the adjoints are important for general linear transformation. For matrices, there is a very simple way of computing it. Just take the transpose. For when you have inner products over reals, you can think about what is the way to do it when you have the field is complex numbers. It's not just a transpose, but actually conjugate transpose. So you conjugate every entry and take the transpose. And that's sometimes referred to just directly as the adjoint of a matrix. It comes from this more general notion of adjoint of a linear transformation. For finite dimensional spaces, we can show that adjoints always exist. They are nice, etc. Before doing that, we will kind of compute something which is sort of for a much simpler linear transformation, which is just a transformation which is mapping vectors to field elements. And again, let's stick to finite dimensional spaces for now, finite dimensional inner product spaces. And so here, yeah, in some sense, let's see. Right. So yeah, you can think of it as kind of adjoint of this very simple transformation. But let's say it's just a way of writing this linear transformation in a different way. It's called a different representation, and hence the name of the theorem. So what this theorem is saying is that the only linear transformation with map vectors to field elements are inner products. That's it. I mean, we saw that the inner product is a linear transformation which maps vectors to field elements when you fix the first input. And this theorem is kind of giving you a converse that that's all there is when you want a linear transformation mapping vectors to field elements. Okay. Okay, so let's prove it. At least, again, this is for the finite dimensional inner product spaces. And again, this is a relatively simple consequence of orthonormal bases, which have many nice properties, and this is one example. So because it's a finite dimensional inner product space, let's say the dimension is n, every finite dimensional inner product space has an orthonormal basis. I'm just using ON for shorthand for orthonormal. So there is an orthonormal basis. Okay. And I claim that's enough to sort of give us what we want. So another thing we know is that to understand what a linear transformation is doing, we just need to understand what it's doing to the basis elements. Okay. So we can completely understand what this linear transformation is just by understanding the values alpha of W1 to alpha of W1. Once you know these, you can compute it on any vector in V. So in particular, any vector V can be written now going back to how we compute coefficients. So we can always compute coefficients this way. We just saw that. And because this is a linear transformation, you can, by linearity, say that this is equal to you can express it in terms of the values of alpha on the basis elements. Okay. And now it's just a matter of collecting things inside. So using the linearity of the inner product in the first coordinate, or the anti-linearity rather. So and this is what we will just call the vector Z. It does not depend on V, it just depends on the values of the linear transformation on the basis elements. And it has the property, and it sort of, this is uniquely defined, and it has the property that alpha of V is just the inner product of Z with, and this is just a consequence of the properties we had for inner products. Okay. So in some sense, yeah, the part we said that inner product is a linear transformation when you fix one of the coordinates, or when you fix the first input. This is pretty much all there is when you're looking at linear transformations from vector spaces to field elements. Again, this is something which can be generalized to Hilbert spaces, not necessarily finite dimensional, because there you're working with this sort of orthonormal basis where you're allowing infinite sums, etc. So you have to be a little careful. And so specifically, you need some property that this alpha is a continuous linear transformation. In particular, if you move the vector a little, the value doesn't change too much of the linear transformation. But once you have this, you can generalize these facts. So it's a convenient way of kind of extending things to the infinite setup. You don't necessarily need these for the course, but yeah, in case you need this for your own research or for any application. Okay. Once you have this, you can also prove the existence of adjoint. Again, let's stick with finite dimensional spaces, and I claim that you can prove that every linear transformation now has a unique adjoint. Again, I'm using some shorthand. This IP spaces is just a shorthand for inner product spaces. And the proof is more or less a direct consequence of what we just said. So now let's try to let's kind of remind ourselves of the property we want from the adjoint. or just the definition, which is the inner product of W with phi of V is equal to the inner product of phi star of W. So it kind of has a flavor that we want some inner product with V, or we want to write something in terms as an inner product with V. Previously, we were doing this, but for a linear transformation, it's mapped to a field element. Now we want to do something like this for, or like we want to do this kind of more generally. And it's actually just applying the previous theorem sort of repeatedly. So just noticing that if you fix a W, then if you look at what this inner product looks like as a function of this V, then it's mapping the vector space to a field element. And I claim that it's a linear transformation. Requires a little bit of a check, but phi is linear in V, and the second and the inner product is linear in its second input. So sort of a composition of two linear transformations, and you can check that it's a linear transformation. But now, because it's a linear transformation, we know that there exists a unique Z, which can depend on W, because this linear transformation depends on W. Z depends on the linear transformation, such that for all V, the inner product of W with phi of V can be written as the inner product with ZW. So it's kind of in the right form. We have inner product with V, but this is sort of the ZW depends on W. So, okay. So let's use this to define what we want. So we are going to say, let's just define phi star of W to be ZW. Okay. For every W, there exists a unique ZW. So there is some vector that exists. We'll just call it phi star of W. And this definitely satisfies the properties we want. So because of what we just said, this is phi star of W. Are we done? Or do we need to prove anything else? We just defined this phi star of W, and in fact, we defined it uniquely because for every W, there exists a unique ZW. So we give a unique definition of this map, which does what we want. Right. So one thing which I claimed that phi star is supposed to be a linear transformation. It's not just any map, but a linear transformation. And that we didn't quite prove yet. So the question we still need to answer is that I claim that that's correct, it is, and that's something which we will need to check. So let's do that. So let's check what phi star of W1 plus W2 looks like, or rather, what the inner product with V is. This is just whatever is Z for W1 plus W2 with V. But then we can also write this as W1 plus W2 inner product phi of V. Now we have the properties of the inner product, which tells us that this can be written as W1 inner product phi of V plus W2 inner product phi of V. And now we again use the properties of the adjoint, that this can be written as, there is a unique Z, so this can be written as ZW1 inner product V plus ZW2 inner product V. And again, using the properties of the inner product, this can be written as ZW1 plus ZW2 inner product V. So we wrote it in two different ways, but the interesting part is that the vector in the two cases is either Z of W1 plus W2, or rather phi star of W1 plus W2, or the sum of two vectors ZW1 and ZW2. But then we said that this vector must be unique in the Riesz representation theorem, because we found it using this orthonormal basis coefficients, etc. So if this has to be unique, then we must have that ZW1 plus W2, rather phi star of W1 plus W2 is equal to ZW1 plus ZW2. So we must have this property, which is needed for linearity. I mean, you also need that the right thing happens when you multiply by a field scalar, that I'll ask you to check. But yeah, once we can check that, we will get a unique linear transformation, which gives us the property that you can write inner products either in the V space or W space, and then you get the same value. Okay? After you just apply the right transformation. Any questions? And yeah, if you notice, it sort of gives us a recipe for computing this kind of adjoints, more generally for any sort of inner product space. So you can go back to the Fibonacci space and think what this means. We'll stop here for today. Just let me mention that there are kind of very nice properties if you know that an operator or a linear transformation from a vector space V to itself, which we called an operator, is self-adjoint in the sense that phi is equal to phi star. For matrices, this corresponds to, at least when A transpose is equal to A, also known as symmetric matrices. And we'll get back to this in the next lecture. But yeah, so these transformations in particular have some very nice properties, which we will prove next time. And then in these properties, kind of all of the things we talked about, eigenvectors, eigenvalues, inner products, orthonormality, all of these come together in a very nice way. And then we'll see this next week. Yeah, let's stop here for today.
I just have one question about,
Yeah, of course.
this was in slide 9 on Parseval's identity.
Okay, let's go there. So, sorry, it's acting up. Okay. I'm not sure what's happening. Let's do it this slow way. Okay.
Yeah, so just, I guess, in the line where you have inner product of UV, the line right under that, I didn't fully understand how it seems like you just added a conjugate to the inner product of WI and U.
Right. So I kind of used the property that inner product is linear in the second input and antilinear or conjugate linear in the first input. So if I had C times W1 inner product, let's say W2 or W1, I can write it as C conjugate times W1 inner product W2, right? Because it's linear in the second input and conjugate linear or antilinear in the first input, right? So now I just did this when I was kind of looking at these inner products of these WIs and WJs. I first separated it into kind of all IJs as separate terms, and then in each IJ, I got an inner product which was really of the form WI inner product U times WI inner product WJ inner product V times WJ. Right?
Okay.
And now kind of to pull out these coefficients and just get an inner product of WI and WJ, I need the conjugate of this one, and this one I can just pull out directly. Right. So when I want to pull out these coefficients, let's call them C1 and C2. I get that I can write this inner product as C1 conjugate times C2 times the inner product of WI and WJ, right?
Yeah. No, I see this. Yeah.
Okay. Yeah, sorry, I just skipped a step, I suppose. So,
All right, thanks.
sure. Anything else? I'll see you all next week or in the office hours.
Thank you.